Namaste dosto. Imagine you're drawing a perfect circle, maybe on your math notebook or while designing a rangoli. Now, what if I told you the circle has special lines and points that make geometry so interesting? Today, we begin by exploring some basic terms that will help us understand circles better. First up, a chord. Think of a chord as a line segment joining any 2 points on the circle's edge, that is, the circumference. If you imagine stretching a string tightly inside a circular ring from one point to another, that string is your chord. Now, the longest possible chord always passes right through the center of the circle. This longest chord has a special name. It's called the diameter star. Next, the center of the circle is that fixed point lying exactly in the middle, equally distant from every point along the circumference. But here's an interesting thing. Not every chord passes through this center point. Some chords float anywhere inside the circle, but they may or may not touch the center. Now, the star of today's show, the perpendicular drawn from the center of the circle to that chord. This perpendicular doesn't just hang out randomly. It plays a unique role by dividing the chord into two equal halves. Sounds like magic? Well, there's a beautiful geometric reason for it. And that's exactly what we aim to prove together. Let's begin with a very important theorem about circles. It states that the perpendicular drawn from the center of a circle to any chord of the circle bisects the chord. In simpler words, if we draw a perpendicular line from the center O of a circle to a chord AB, then that perpendicular meets the chord at its midpoint. So, if the perpendicular from the center is OM, and it meets the chord AB at M, we can say that AM equals MB. This theorem is widely used in coordinate geometry and in geometric constructions. Interestingly, the theorem can also be reversed. If a line from the center divides a chord into two equal parts, then that line is perpendicular to the chord. Let's now prove this step by step. We have a circle with center O and a chord AB. A perpendicular OM is drawn from the center to the chord, meeting it at point M. Now, let's look at the two triangles, triangle OMA and triangle OMB. First, OA equals OB, because both are radii of the same circle. Second, OM is common to both triangles. And third, angle OMA equals angle OMB equals 90 degrees, since OM is perpendicular to AB. Therefore, by the right angle hypotenuse side congruency rule, we can say that triangle OMA is congruent to triangle OMB. By congruency, the corresponding sides are equal. Hence AM equals MB. So we have proved that a perpendicular drawn from the center of a circle to a chord bisects the chord. Now that we've seen the proof, let's check how this theorem helps us. Here comes the practical side of geometry. You can use this property to construct the perpendicular bisector of any chord. How? If you know just a part of a circle like an arc or a chord, you can find the center by drawing these perpendiculars from chords. Very handy during constructions on paper or with software. It's also useful in problems involving symmetry. For example, if you want to determine the diameter of a circle or check if several lines intersect at a single point inside the circle, this theorem gives you a reliable geometric tool. Additionally, it plays a critical role in proving properties about cyclic quadrilaterals which are four-sided shapes inscribed within the circle. Since chords form the sides of these quadrilaterals, knowing how chords behave helps solve many geometry problems. And don't forget the connection with tangents This theorem assists in constructing the exact midpoint of a chord, which in turn helps define the radius and tangent relationships precisely, especially when using compass and ruler for neat constructions. So, this isn't just theory. It's a toolbox for many circle problems. Let's bring this theorem down to earth with an example. Shabash for those who love numbers. Suppose the chord AB is 10 centimeters long inside a circle with center O. The radius, that is, the length OA and OB, is 6 centimeters each. We drop a perpendicular from O to AB at point M, where OM is perpendicular to AB. We want to verify. Does OM bisect AB? Meaning, is AM equal to MB? Using what we have learned, triangles OMA and OMB fulfill the RHS congruency rule. O equals OB, OM is common, and the angle at M is 90 degrees. So, the two triangles are congruent. Therefore, AM equals MB. Since AB is 10 centimeters, each half measures 5 centimeters. That is, AM equals 5 centimeters and MB equals 5 centimeters. The chord AB is perfectly bisected by the perpendicular from the center. So, from given to proven, AM equals MB equals 5 centimeters. This neatly confirms our theorem with actual numbers. Excellent. Before we wrap up, there's an important twist, the converse theorem. Let's see what it says. If a line drawn from the center bisects a chord, then that line must be perpendicular to the chord. In simpler words, if the segments AM and MB are equal, the line OM is at right angles to AB. Why does this happen? This is because the two triangles OMA and OMB still are congruent, with O equals OB, OM shared, and M equals MB given. Congruent triangles mean equal corresponding angles. So angle OMA equals angle OMB. If these two angles are equal and lie on a straight line, they must both be right angles, that's 90 degrees each. Hence, the line from the center is perpendicular to the chord. This converse is very useful in solving problems because it lets you work backwards. If a center line halves a chord, you automatically know it's perpendicular, even if you weren't told upfront. Pretty cool, right? Let's take a minute to recap what we learned today. 1. When you draw a perpendicular from the center of a circle to a chord, it bisects the chord. This means it divides the chord into two equal parts. 2. The converse is also true. If a line from the center bisects a chord, then that line is perpendicular to the chord. 3. Our proof used the RHS congruency rule. Triangle OMA is congruent to triangle OMB, which gave us M equals MB. Key ideas to remember. The perpendicular from the circle's center always bisects the chord, and we proved this beautifully by comparing triangles using radii and right angles. The converse extends the power of this property, making it even more useful in geometry constructions and problem solving. So next time you see a circle with chords, think about the center and the magical right angles drawing that split chords evenly.